So in this series of videos, I'll be talking about proof by mathematical induction, or just simply put, proofs by induction. So let me give you a definition first. Okay, so for this definition, I'm going to use kind of a weird notation. So I'm going to call a mathematical statement Pn. Okay, so Pn is sort of what's called a predicate function, but you don't need to know about that. I'm calling a mathematical statement Pn. So for example, it could be n is even, or something like n is a multiple of 7. So anything with a mathematical meaning, or something that seems like it needs to be proved, having of course n in it, where n is an arbitrary integer, arbitrary integer. Okay, so that's just before we start defining induction, I just want to give you that kind of notation. So it's basically any mathematical statement. Okay, so there are two steps to a proof by induction. So proving Pn. So Pn by mathematical induction. Okay, so there's two steps. So step 1 is called the basis step. Or basis case. Doesn't really matter. So in the basis step, you prove for the smallest n. Okay, so what I mean by that, you evaluate your statement Pn at the smallest applicable value of n. So for example, if I tell you the statement 2n is even for n greater or equal to 1, okay, well, your basis step will just be showing that 2 times 1 is equal to 2, which is clearly even. Okay, so that's your basis step. Okay, now the second, and probably the most important step, is the inductive step. So in the inductive step, what you do is you assume that the statement, remember Pn is a statement, that the statement Pn is true. So that is, you're assuming that Pn is going to be true no matter what n. And what you want to do, well, no matter what n, depending on the restriction, and what you want to do is you want to prove, that Pn plus 1 is also true. Okay, so I'm not going to give you an example for that because that would take a lot of time. I'm basically just going to give you a straightforward example to cover both of these things. Okay, so two steps to mathematical induction: the basis step and the inductive step. Okay, so let me give you an example. So prove that Pn is true. So prove that the statement Pn is true, where Pn is the statement that sigma of n equals 1 to k of n. So that is adding 1 plus 2 plus 3 until k. So that is equal to k times k plus 1 over 2. So that's what I want to prove. Okay? So what do I have to do in a mathematical induction, in a proof by mathematical induction? So first, what I need to do is I need to do my basis step. And I actually forgot to mention in this question that this statement applied for n greater or equal to 1. Okay, so I'm trying to prove the statement Pn for n greater or equal to 1. Okay, so my basis step in this case is the lowest possible integer that's assumed or sort of implied in this question. Okay, so in this case it would be prove that the statement, remember P of n is a statement, so P of 1 is just the same, it's just evaluating the statement P at the integer 1. So prove that P1 is true. Okay, so how I do this is, you can do this several ways, but what I like to do is I like to prove the left hand side and the right hand side and then just show that both are equal. So the left hand side in this case is just going to be 1, because I just need one term. Okay, so because the left hand side statement would be the sigma from n equals 1 to 1 of n, so that's just 1, so the left hand side is 1. Then my right hand side, I would need to evaluate k at 1, so that's what I'll do. I'll write 1 times 1 plus 1 over 2, and that's equal to 2 over 2, and that's equal to 1. So clearly you can see that the left hand side is equal to the right hand side, and so I've proven the basis step, or the basis case. Okay, that's supposed to be a tick. There we go. Okay, now the inductive step is a bit trickier because of the basis step. The inductive step. So what I do in the inductive step, I assume that Pn is true. So in other words, i.e., that is that sigma n equals 1 to k of n is equal to k plus 1 over 2. So I'm assuming that this statement here is true. I'll actually rewrite this one more time so it's clear. So that just means that 1 plus 2 plus dot plus k is equal to k times k plus 1 over 2. Okay, so that's what I'm trying to show. But in this case, I'm assuming that this is true. Okay. All right. Now, after assuming that this is true, what I want to do, I want to prove. So this is my goal. Prove that P n plus 1 is true. P n plus 1 is true. Okay. So basically, what I want to do is I want to show that n plus that n equals 1 to k of n. It's actually n plus equal 1 sigma n plus 1 k plus 1. Yeah, of n is equal to. So the reason why I added the k plus 1 here is because I'm adding an extra element, an extra integer to my statement Pn. Okay, so now it's no longer the sum from 1. It's no longer the sum from 1 to k. It's now from 1 to k plus 1. 1 to k plus 1 of n. So I wanna show. So this is what I'm trying to show. I want to show. So I'll put a question mark for it to be a bit clearer. So this is what I want to show. I want to show that the left hand side is equal to k plus 1. Since I'm just adding, I'm just applying k plus 1 or n plus 1 to wherever I see my variable. So is equal to k plus 1 times k plus 2 over 2. Okay? So if you're a bit confused on why I wanted to prove that, okay, just think of what I'm trying to do in an induction. I'm assuming that my nth term, that my term until n is true, okay? And then I'm trying to show that my statement is true for the n right after, okay? So this is, I'll put this as an aside as to why I'm doing this. So I know that 1 and 2, then all the way to n, I know that p of this is true, okay? What I want to show is that n plus 1, that n plus 1 applied to p, n plus 1 applied to p is also true. So this is my goal. I want to show that p of n plus 1 is also true. Okay. So prove that p n plus 1 is true. Okay, so this is my statement. I'm going to rewrite this again. So what this means is that 1 plus 2 plus 3 plus dot 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 plus k plus, and this is the term that I'm adding, plus k plus 1. So this is, notice this is just the following integer after k. So I want to show that that's equal to k plus 1, k plus 2. So this is my statement p n plus 1 or k plus 1. It really doesn't matter. N is just a dummy variable. So I'm trying to show this, okay? So what I do is I start with my left-hand side, okay? So my left-hand side here is 1 plus 2 plus 3 plus dot 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 plus k plus 1. Okay, so that's my left-hand side. And if you're quick enough, if not, it doesn't really matter, but if you're quick enough, you'll notice that this here is something that I already have. I already have in my assumption that 1 plus 2 plus dot 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 plus k is equal to k plus 1 times k over 2. So I can there's no problem if I just substitute this as this thing here. So that's what I'm going to do. So the left-hand side is now equal to k times k plus 1 over 2 plus k plus 1. Okay, and this has a special name. This is called the inductive hypothesis. It's called the inductive hypothesis. Okay, so now it's basically just algebra. Remember what I'm trying to prove? I'm trying to prove that this side over here, I'll use a different color, that this side over here is equal to this. So I'm starting here, and what I want to do is I want to end at this thing. I want to end at k plus 1 times k plus 2 over 2. Okay, so I'll do some, let's start by doing some foiling. So that's k squared plus k over 2, and that's just, let me put on the same denominator, so I'll put this 2, k plus 1 over 2. And now let's add those two together, so k squared plus k plus 2 k plus 1 over 2. And I'll FOIL the 2, so I'll distribute it, which will give me k squared plus k plus 2k plus 2. Actually, I could have avoided doing that, but whatever, it's just to be clear. So now what I'm going to do is I'm going to factor k. So I factor k, and that leaves me k times k plus 1, plus I factor 2 again, 2 times k plus 1 over 2. And so k plus 1 is common, so you know already that that's equal to k plus 1 times k plus 2 over 2. And look what we have here. It's the right-hand side that I was trying to get to. So I've shown that the left-hand side is equal to right-hand side. So what I can conclude now is I can conclude that by mathematical induction, conclude that sigma of n equals 1 to k of n is equal to k times k plus 1 over 2. And that's basically the whole idea of mathematical induction.